Welcome to another deep dive. Today we're going to be stepping into a world that's as intricate and fascinating as the workings of a magic wand.
All right.
It's the particle model of matter.
Okay.
You know, that fundamental idea in physics that explains how everything around us is made up of tiny, constantly moving particles.
Right.
It might sound a bit like a complicated potion recipe, but trust me.
Yeah.
By the end of this deep dive, you'll be seeing the world in a whole new light, and guiding us through this microscopic universe is our expert,
Oh, wow.
who's got a knack for making even the tiniest particles seem captivating.
Well, it's great to be here. I'm always excited to delve into the world of particles.
Yeah.
They may be small, but they hold the secrets to so much of what we see and experience every day.
Exactly. It's like discovering the hidden magical properties of seemingly ordinary objects.
Right.
Kind of like finding out a seemingly plain quill actually holds the secret to writing with invisible ink.
Yeah.
First off, let's talk about something that's pretty basic, but super important.
Okay.
Density.
Okay.
Think of it like this. Imagine 2 galleons, those magnificent wizarding ships.
Okay.
One is filled to the brim with gold from Gringotts, and the other is packed with feathers
Right.
from a flock of fluffy whoopers.
Oh, wow.
They both take up the same amount of space, but which galleon do you think would be heavier?
That's a great way to visualize it. The galleon filled with gold would be significantly heavier.
Right.
And that's because gold is much denser than feathers.
Okay.
Density is all about how tightly packed matter is within a given space.
Mm-hmm.
In other words, how much mass is crammed into a particular volume.
So it's like comparing a tightly packed trunk full of heavy textbooks for Hogwarts
Yeah.
with a trunk filled with light, fluffy scarves.
Right.
The scarves take up the same space,
Mm-hmm.
but don't weigh nearly as much.
Exactly. And this difference in density all comes down to those tiny particles we were talking about,
Okay.
atoms and molecules.
Right.
In a dense material like gold, the atoms are packed very closely together, almost like a crowd of witches and wizards jostling for the best view at a Quidditch match.
While in something less dense, like feathers or those fluffy scarves,
Yeah.
the particles are more spread out with lots of empty space between them.
Mm-hmm.
Kind of like when the Hogwarts students are enjoying a leisurely afternoon on the grounds.
That's a perfect analogy.
Yeah.
And you know, this concept of particle arrangement is key to understanding the different states of matter.
Okay.
Solids, liquids, and gases.
Okay, let's dive into that.
Okay.
It's like exploring the different forms a magical creature can take.
Right.
Sometimes solid and tangible,
Mm-hmm.
other times fluid and ethereal, or even completely invisible, like a ghost.
Imagine those Hogwarts students again.
Okay.
If they're huddled together in a tight formation, barely moving,
Yeah.
that's like the particles in a solid. They're packed closely, vibrating a bit,
Mm-hmm.
but mostly staying in their fixed positions. Now, if those students loosen up a bit and start milling around,
Okay.
flowing around each other, but still staying relatively close, that's like the particles in a liquid.
And if they're suddenly released from class and scatter across the grounds,
Yeah.
running and zooming about with tons of space between them,
Right.
that's like the particles in a gas.
You've got it. And because of those different arrangements of particles, solids are generally the densest,
Okay.
followed by liquids, and then gases being the least dense.
Mhm.
Of course, as with anything in the world of magic and science, there are a few exceptions.
Oh, I love exceptions.
Right.
They're like those rare magical creatures you only hear whispers about.
Mm-hmm.
What kind of exceptions are we talking about?
Well, think about ice.
Okay.
It's a solid form of water, so you might expect it to be denser than liquid water.
Right.
But as we all know, ice floats.
Right. That's why those ice sculptures at the Yule Ball don't just sink to the bottom of the fountain.
Exactly.
But how can ice be less dense than water if they're both made of the same molecules?
It all comes down to how the water molecules arrange themselves when they freeze. Instead of packing tightly together, they form a more open crystalline structure with more space between them.
All right.
It's like when those Hogwarts students carefully arrange themselves into a complex formation for a special event.
Yeah.
They take up more space than if they were just huddled together randomly.
So the arrangement of the water molecules in ice is like a perfectly choreographed dance,
Yeah.
creating a beautiful structure that's actually less dense than the liquid form.
Right.
It's like discovering that a seemingly delicate snowflake is actually stronger than it looks.
Exactly. And this unique property of water is incredibly important for life as we know it.
Yeah.
Because ice floats, it forms a protective layer on top of lakes and oceans,
Right.
insulating the water below and allowing aquatic creatures to survive even in freezing temperatures.
Yeah.
If ice were denser than water, it would sink.
Okay.
And bodies of water could freeze solid, which would have disastrous consequences for the entire ecosystem.
That's amazing. It's like those seemingly small details in the wizarding world that end up having huge implications. You know, like how a tiny drop of phoenix tears can heal even the most serious injuries?
Precisely. And speaking of changes, this leads us perfectly into another fascinating aspect of the particle model of matter changes of state. Welcome back to our exploration of the particle model of matter. It's like we've stepped into a hidden room in Hogwarts filled with bubbling cauldrons and enchanted ingredients, ready to uncover the secrets of how matter transforms.
Exactly. Last time we were talking about how those tiny particles, atoms, and molecules are arranged in solids, liquids, and gases. But those particles aren't just sitting still, are they?
No.
They're like little bundles of energy constantly moving and shaking.
You're absolutely right. And the amount of energy those particles have determines what state the matter is in. It's like the difference between a calm, peaceful unicorn and a fiery Hungarian horntail dragon.
Okay, I can picture that. The unicorn with its gentle energy represents a solid, while the fiery dragon full of restless energy represents a gas.
Exactly. And just like a wizard can use magic to transform objects, we can use heat energy to transform matter from one state to another.
So it's like casting a spell to change the form of something, but instead of incantations, we're using heat.
Precisely. Take melting, for example. When you heat ice, you're giving those water molecules more energy. They start to vibrate faster and faster, like a bunch of Hogwarts students getting excited about a Quidditch match.
And eventually, they have enough energy to break free from their rigid structure and start flowing around each other, turning from solid ice into liquid water. It's like watching those students spill out of the stands and onto the field, moving more freely.
That's a great way to visualize it. And the same principle applies to other changes of state. When you boil water, you're giving the water molecules even more energy, causing them to move so fast that they escape into the air as steam.
So it's like those water molecules are graduating from Hogwarts, soaring off into the world as free-spirited gas particles. But here's something I've always wondered about. When matter changes state, does the amount of matter actually change? Like if I were to magically transfigure a teapot into a toad, would the amount of matter remain the same?
That's a fantastic question, and it highlights a fundamental principle, conservation of mass. Just like in transfiguration, the total amount of matter always stays the same during a change of state. It doesn't disappear, it simply changes form.
So it's like the ingredients in a potion. They might transform and combine, but you always end up with the same amount of matter in the end.
Exactly. Now let's delve a little deeper into the energy involved in these changes of state. You mentioned casting spells earlier, and in the world of physics, we have specific terms for the energy involved in these transformations.
I love learning new spells. I mean, physics terms. Tell me more.
Well, there's something called latent heat, which is the amount of heat energy required to change the state of a substance without changing its temperature. It's like a hidden energy barrier that needs to be overcome before a transformation can occur.
Okay, I'm intrigued. Can you give me an example?
Imagine you're melting a cauldron full of chocolate for a delicious potion experiment. You keep adding heat, but the chocolate stays at the same temperature until all of it has melted. That's because the heat energy you're adding is being used to break the bonds holding the chocolate molecules together in their solid form, allowing them to flow freely as a liquid.
So it's like that heat energy is working behind the scenes like a house elf, tirelessly cleaning up after a messy potion experiment? But instead of cleaning, it's breaking those molecular bonds.
That's a fantastic analogy. And once all the chocolate has melted, any additional heat you add will then start to increase the temperature of the liquid chocolate.
So it's like the house elf has finished its invisible work. And now the heat can focus on raising the temperature.
Fascinating.
But tell me, is the amount of latent heat the same for all changes of state?
Great question. The amount of latent heat varies depending on the substance and the specific change of state. We have specific terms for the latent heat involved in different transformations.
Hit me with those physics spells.
For melting or freezing, we call it the latent heat of fusion. And for boiling or condensing, we call it the latent heat of vaporization.
So melting and freezing have one latent heat value. While boiling and condensing have another. It's like different levels of magical energy are required for different transformations.
Exactly. And these values differ depending on the substance. Water, for example, has a relatively high latent heat of vaporization,
Huh?
which is why it takes a lot of energy to boil water and turn it into steam. That's one reason why steam is so powerful and can be used to drive engines and turbines.
It all makes sense now.
Yeah.
We've gone from visualizing those tiny particles to understanding how they behave when we add or remove heat. Like we've learned to control the energy flow of matter, just like a skilled wizard channeling their magical power.
And there's even more to explore. But before we delve into the concept of pressure, let's take a moment to reflect on what we've learned so far.
Okay.
What stands out to you as particularly interesting or surprising?
I think what fascinates me the most is how those seemingly simple changes of state, like melting or boiling,
Yeah.
actually involve these intricate energy exchanges and molecular transformations. Like those everyday phenomena we take for granted
Right.
are actually fueled by invisible microscopic magic.
That's a great observation. And it highlights how understanding the particle model of matter can give us a deeper appreciation for the world around us. Even the most ordinary things, like a melting ice cube or a boiling kettle,
Yeah.
become fascinating when you consider the intricate dance of particles at play.
Very back and ready to tackle the next big concept in our particle model of matter adventure.
Right?
Pressure. It's like we're about to enter a restricted section of the Hogwarts library,
Right.
filled with ancient texts about forces and invisible energy.
Yeah.
Okay, I'm ready to be enlightened.
Yeah.
But first, can you give us a quick recap of what pressure actually is? It's like an invisible force pushing on things.
Right. Exactly. Remember how we've been talking about those tiny particles
Yeah.
constantly moving and colliding with each other and their surroundings?
Right.
Well, pressure is the force exerted by those particles when they bump into things.
Okay.
Imagine a crowd of excited Hogwarts students pushing their way through a narrow corridor.
Yeah.
Each individual student exerts a small force,
Right.
but together they create a significant push.
So the more students or particles there are in a given space,
Right.
the more collisions they'll have and the higher the pressure.
Exactly.
It's like trying to cram all of Hogwarts students into a tiny broom cupboard.
Yeah.
Things will get pretty squished.
Precisely. And just like the excitement level of those students can vary, the energy of those particles can also change, which affects the pressure.
So if those students are super hyped up for a Quidditch match,
Right.
they're going to be bouncing off the walls even more, creating even more pressure.
That's a great analogy. When we heat a gas, its particles gain more kinetic energy and move faster,
Right.
leading to more frequent and forceful collisions, which increases the pressure. It's like heating a cauldron over a roaring fire.
Okay.
The potion inside starts bubbling more vigorously as the pressure builds.
Okay, that makes sense.
Right.
But how does the volume of the container affect pressure?
Right.
Does it matter if those particles are bouncing around in a tiny vial or a giant cauldron?
It absolutely does. And this relationship between pressure and volume is described by a fundamental law in physics known as Boyle's law.
Ooh, another physics spell to add to my repertoire, Boyle's Law. Tell me more.
Boyle's law states that for a fixed mass of gas at a constant temperature,
Oh, wait.
the pressure and volume are inversely proportional. In simpler terms, if you decrease the volume of a container,
Right.
the pressure of the gas inside will increase and vice versa.
So it's like squeezing a balloon. The smaller you make the balloon, the harder the air inside pushes against the walls, increasing the pressure.
Right.
But if you let the balloon expand, the pressure decreases.
Exactly. And this principle is used in countless applications,
Yeah.
from bicycle pumps and air compressors to scuba diving equipment and even the way our lungs work.
Wow. It's amazing how those tiny invisible particles can exert such a powerful force. It's like discovering that a seemingly simple charm can actually have a huge impact on the world around us.
Absolutely. And understanding pressure is essential for understanding many other concepts in physics, chemistry, and even biology.
Well, I feel like we've unlocked a whole new level of understanding about the world around us. We've gone from picturing those tiny particles to understanding how they behave in different states of matter.
Right.
How they interact with heat energy.
Yeah.
And how they create pressure.
It's like we've completed a challenging potions class,
Right.
learned some new spells, physics laws,
Yeah.
and gained a deeper appreciation for the magical world of matter.
Exactly. And just like a young witch or wizard graduating from Hogwarts, we're now equipped with the knowledge and tools to continue exploring the wonders of science. Who knows what other secrets we might uncover in our future deep dives?
The possibilities are endless. And remember, just like in the world of magic, there's always more to learn and discover in the realm of science.
So to all our listeners out there, keep that curiosity burning bright. Keep asking questions and keep exploring the magic of the world around you. Who knows, you might even stumble upon a groundbreaking scientific discovery yourself.